Total internal reflection and critical angle. Pencil on the slide indicates where you may wish to take notes as you're following the video. Key areas: critical angle and total internal reflection. What we will do today: state what is meant by total internal reflection and critical angle, state the relationship between refractive index and critical angle, and carry out calculations on the above. Revision from refraction. In the previous video, we looked at the refractive index, and we saw that the refractive index n of a material is equal to the ratio sine theta 1 over sine theta 2, lambda 1 over lambda 2, v1 over v2, where the 1 denotes air. So for example, theta 1 is the angle of incidence in air, theta 2 is the angle of refraction in a medium, lambda 1 is a wavelength in air, lambda 2 is the wavelength in the material, v1 is the speed in air, approximately the same as speed in the vacuum, and v2 is the speed within the medium. Fundamentally, Snell's law states that n, the refractive index, is equal to sine theta 1 over sine theta 2. We can also express this as n2 over n1 is equal to sine theta 1 over sine theta 2, noting that the refractive index of air is 1. In the experiment that we would conduct in order to investigate critical angle, we would draw around a semicircular block, draw in the normal line through the center, shine a light ray along the normal to the center of the block, and then continue to shine this light ray at the center and slowly move the light ray outwards with an increasing angle of incidence. We then keep going until the angle of refraction is equal to 90 degrees, as shown in the second diagram. At this point, it's important to note that we will likely see some partial reflections. The critical angle is measured as the angle at which light incident inside of the block will refract out at 90 degrees to the normal, that is along the surface. Total internal reflection. In diagram 1, we can see that light is being refracted out of the semicircular block. In diagram 2, light is refracted at 90 degrees. The angle of incidence in this case is called the critical angle. In diagram 3, we can see that in any angle greater than the critical angle, we will see total internal reflection. The critical angle. The critical angle, theta c, is the angle of incidence when the angle of refraction is 90 degrees. It is the smallest angle of incidence above which total internal reflection occurs. It is often given the symbol theta c. Total internal reflection. This takes place when all of the light ray is completely reflected and none of it is refracted. Remember, when measuring the critical angle, we will see refraction out at 90 degrees to the normal, and there will be a partial reflection. In total internal reflection, all of the light ray is completely reflected. Total internal reflection takes place at angles above the critical angle, as we can see in the diagram here. Our normal reflection rules count, which means the angle of incidence is going to be equal to the angle of refraction. Curved surfaces. Note that there is no refraction at a curved surface, because a radial ray, as you may know from maths, strikes a surface at a normal incidence. That is, a ray acting towards the center of the block will always enter the surface at 90 degrees to the surface, that is, along the normal line. And we're aware from our previous work with refraction that if light enters into a different material along the normal line, although it will experience refraction, that is, its speed will decrease, there will be no change in direction. This is why a semicircular block is used to find the critical angle. From National 5, we looked at a number of different uses for total internal reflection. Total internal reflection is used to send light signals along optical fibers, and this can be used to send telecommunications such as internet, TV, and phone. We use optical fibers for our broadband internet, and this is how Virgin Media, for example, provide their services. The relationship for critical angle and refractive index is shown in the box here. N is equal to 1 over sine theta c. And that's because n is equal to sine theta 1 over sine theta c, theta 1 being the angle in air. When the angle in air is 90 degrees, as we see in the critical angle, then that's going to be equal to 1. Example. In a material, its refractive index is 1.4, and you need to find the critical angle. We use the relationship n is equal to 1 over sine theta c. And so 1.4 is equal to 1 over sine theta c. Theta c can be found by rearranging to sine theta c is equal to 1 over 1.4, and then theta c itself is the inverse sine of 1 over 1.4. In this example, that gives us a critical angle of 45.6 degrees. Look at the Old Hire 2008 paper, question 16. The value of the absolute refractive index of a diamond is 2.42. You should note that values of absolute refractive index are given on the data table at the front of the paper. We're asked to find the critical angle. So in order to find the critical angle, we use the relationship n is equal to 1 over sine theta c. Sine theta c is equal to 1 over n. Theta c is equal to the inverse sine of 1 over n. Now that relationship is not on the relationship sheet, but it's really useful to remember because this is a very common multiple choice question. In this case, sine theta 1 over sine theta 2, or 1 over sine theta c, can be used with 2.42 to find that the critical angle is equal to 24.4 degrees, which is B. 2009, question 15. Similar question. A ray of monochromatic light passes into a glass block as shown. The refractive index of the material is. So here we can see from the diagram that we must be at the critical angle because light is being refracted at 90 degrees to the surface. So 33.5 degrees is the critical angle. Remember our equation, 1 over n is equal to sine theta c. So n is equal to 1 over sine theta c. In this case, 1 over the sine of 33.5. 1 over the sine of 33.5 is equal to 1.81, which is E. So in the 2001 paper, question 27b, you have a ray of monochromatic light passes from air into a block of glass as shown, and you need to use the information from the diagram to show the refractive index of the glass for this light is 1.61. The skill here is identifying what is the angle of incidence and what is the angle of refraction. So the angle of incidence, remember, is measured between the incident ray and the normal, so that's our 47 degrees here. That's our theta 1. The angle of refraction is measured between the refracted ray and the normal, so that's this one here. That's our theta 2. Remember, theta 1 is always the angle in the less dense medium. So n is equal to sine of theta 1 over sine of theta 2, which is equal to the sine of 47 divided by the sine of 27 which is equal to 1.61. Remember, for refractive index, there's no units. You're then asked to show by calculation whether the ray is totally internally reflected at point X. So we know what the refractive index is. N is equal to 1.61. We need to find the critical angle. The formula on the relationship sheet is 1 over sine theta c is equal to n. But I'm going to rearrange that. I'm going to say that theta c is equal to the inverse sine of 1 over n. So although this isn't on the relationship sheet, it's a very common question. It's a useful equation to remember. Substituting the values, sine to the minus 1, 1 over 1.61 is equal to 38 degrees. So at point X, we can see that the angle of incidence, remember, is measured between the normal and the incident ray, is 63 degrees. 63 degrees is greater than the critical angle of 38 degrees. So that means total internal reflection takes place. So 2002 paper question 27, a ray of red light is directed at a glass prism of side 80 millimeters as shown in the diagram below. Use the information from this diagram to show that the refractive index of the glass for this red light is 1.52. So again, just like in the previous question, we need to identify our angles of incidence and angles of refraction. The angle of incidence is here, our 20 degrees, measured between the incident ray and the normal. So that's our theta 1. Our angle of refraction is the 13 degrees, measured between the refracted ray and the normal, and that's our theta 2. So n is equal to the sine of theta 1 over sine theta 2. Substituting the values, sine of 20 over sine of 13 is equal to 1.52 as required. So continuation from the previous question, we're asked to say what is meant by the term the critical angle. So the critical angle is the angle of incidence above which total internal reflection will take place. So if the angle of incidence is any value above the critical angle, the rays of light will be totally internally reflected. You're then asked to calculate the critical angle for the light in the prism. I'm going to use that equation again that's useful. Theta c is equal to the inverse sine of 1 over n. From the previous question, n was 1.52, so 1 over 1.52 here, giving us a value of 41.1 degrees. We're then asked to sketch a diagram showing the path of the ray of red light after it leaves the prism, marking on the diagram the values of all relevant angles. So we need to identify the new angles of incidences when we're striking the surface at this side here. That will allow us to determine if the light is refracted out or totally internally reflected. If it's refracted out, we simply need to mark the angle of incidence and the angle of refraction. If it's totally internally reflected, we need to mark the angle of incidence, the reflected angle, and also find the path as it exits the block. So let's have a look at this diagram in a little bit more space. First thing we're going to do is we're going to draw a normal line. at 90 degrees to the surface. Internal angles of a triangle is 180. So we have 60, 77 within the top triangle. So this angle here is going to be 180, take away 60, take away 77, which is equal to 43 degrees. So this angle here is 43 degrees. The angle here is going to be 90 degrees, take away 43, which is equal to 47 degrees. Now we previously calculated that our critical angle is equal to 41.1 degrees, which means that our light is going to be totally internally reflected. So our angle here is going to be 47. This is going to be reflected. You want to make sure that it looks pretty much the same as it's reflected. This is 47 degrees. Now if this is 47 degrees, again, we can calculate this angle inside. That's going to be 43 degrees, which means we can draw another normal here at 90 degrees to the surface. We know that this is 43 degrees, this is 60 degrees. We can work out the angle here. 180, take away 60, take away 43, gives us 77 degrees, meaning our angle of incidence here is 13 degrees. 13 degrees is definitely less than 41.1, so refraction takes place. Remember, when we refract, we move away from the normal because we're coming into a less dense medium. So here's our refracted ray. And by using n is equal to sine theta 1 over sine theta 2, we can work out what this angle is here. So this is angle x. Angle x is the angle in air, so 1.52. The refractive index we had in the question is equal to sine x over sine 13, because 13 is our angle of incidence. X is equal to the inverse sine of 1.52 multiplied by sine 13, which is equal to 20 degrees. So I've shown all of the angles that are relevant. In an exam, you would use a ruler to make sure these lines are nice and straight. It's important that I'm showing the light inside of the block, and I'm also showing the light refracting out of the block. This is as difficult as it gets. This is the most difficult example of a question on refraction you can get. And the beauty of this question is it goes through all the different parts. Working out the refractive index, working out the critical angle, using the critical angle to predict the path of light within the material. If you can do this question, you can do any question of this type. Revised Higher 2014 paper, question 15. We're combining two bits here. So we're given the diagram with the different angles. We're asked to find the critical angle. In order to find the critical angle, we need to find the refractive index first. So n is equal to sine of theta 1 over sine of theta 2. Identifying theta 1 and theta 2 correctly, remember angle of incidence measured between the incident ray and the normal. So here's my theta 1. Refracted ray measured between the refracted ray and the normal. This is theta 2. N is equal to sine of 46 divided by sine of 28, which is equal to 1.53. We're not done yet because we're asked to find the critical angle. Again, I'm going to use that shortcut equation. theta c is equal to the inverse sine of 1 over n, which is equal to the inverse sine of 1 over 1.53, which is equal to 41 degrees. Here are some other questions that you can try out to improve your abilities within refraction. Looking at the revised higher paper 2012, question 29, and 2013, question 29.